Hello. So in this second video on blockchain basics, I would like to talk about cryptography. So cryptography is often misunderstood, and as it forms the basis of a lot of blockchain related technology, I think it's important to understand before we actually go into detail on how the blockchain actually works. So yeah, let's just introduce cryptography. So classic cryptography is what most people think about when they hear cryptography. And you can see here these Enigma machine and this cryptography disk, the cipher disk. These were sort of classic devices focused on keeping secrets. So though the idea many people have of cryptography, and for centuries that was how cryptography works, was to have sort of a cipher and to encrypt a secret in order to transmit a message secretly for military use or whatever. And that usually operates on text. You can see here there's letters mapped from one alphabet to another. So that's classic cryptography. But when it comes to modern cryptography, which is the cryptography we use these days in computer science, we obviously operate on numbers because computers always work with numbers. But that's not the main difference. The main difference is really the purpose of the cryptography. And there's three main goals the modern cryptography has. And that's confidentiality, integrity, and authenticity. So in terms of confidentiality, that's really carried over from classic cryptography. And the main idea here is to keep a secret. So that's encryption, decryption, and basically transforming a plain text into a ciphertext and transmitting it securely over an unsecure link. Now, that's the type of cryptography that is usually not used in blockchains. And the other two properties are more important for us in this course, and that's integrity and authenticity. So integrity is the insurance that a piece of data has not been altered. So what cryptography tries to do in this sense is to have some form of checksum or message digest that can prove to the receiver of the message that the piece of data being sent has not been altered, or the piece of data being stored on some server is still in the original form and has not been altered. And that's what message authentication codes do, and that's what hashing algorithms do, which are frequently used in blockchains. So then there's authenticity, which is the third desired property, and that's the authenticity of a message in terms of who is the sender of a message or who has created a piece of data. Basically, it allows to verify the origin of message, and that's provided by what we now know as public key cryptography, and it's the basis of digital signatures. So this basically means you sign a piece of data to ensure that it's that you can identify the author of the data. And as a side effect, digital signatures and public key cryptography usually also prove integrity, that the data has not been altered. So integrity and authenticity often go together. And these two are really what we need from cryptography and blockchain technology. So when people think of cryptography, they often think about symmetric encryption or secret key cryptography, which is very important, but generally not used in blockchain. But for completeness, we'll introduce it here. So the idea is there's a message that Bob tries to send to Alice, and that's encrypted with a secret key, and Alice uses the same secret key to decrypt the message. So that's very simple, secret key like a key phrase or something like this. And the problem with this is obvious, that how do you get the secret key from Bob to Alice? And that was a big problem in classic cryptography and even in modern cryptography until the 1970s. Which has been solved by something called public cryptography. But anyway, symmetric encryption has its uses. It's used a lot, for example, for encrypting your disk drive, that sort of thing. And even in communication, usually we use public cryptography to encrypt a secret key and then use more efficient symmetric encryption to do the actual cryptography, the actual encrypting and decrypting of the message. But anyway, public key cryptography is sort of what solved the message, the key transmission problem. And the way public key cryptography works, it's asymmetric. And in this case, each key is a key pair, really. So Bob and Alice both have a public and a private key. And, Bob's public key, or Alice's public key in this example that is on the screen here, is freely distributed. It's publicly known. So Alice can just send her public key to Bob and anyone else and doesn't have to be worried about that being intercepted. So Bob can then, or anyone else, send a secret message to Alice by encrypting using this public key. And Alice also has a corresponding private key, which she can use to decrypt Bob's message. Now, obviously, Alice's private key can never be shared, otherwise the system is unsafe. But the beauty of this is that, it doesn't have to be shared. The only thing that has to be sent over a communication link is a public key, which can be as secure or as insecure as it wants. The communication link can be insecure. That's not an issue if the key is intercepted. So that sort of key, asymmetric encryption and public key cryptography is very powerful. And it's not just powerful because it provides this key transmission property, but also because it can be used for something like digital signatures. And in that case, it's just done in the inverse. The public-private key pair can be used in inverse, and you can basically imagine Alice encrypting something using her private key and sending this to Bob. Then Bob can use this Alice's public key or anyone else to decrypt the message. And the side effect here is not that the message is secret, but it's to prove using this property, inverse encryption, so to speak, that Alice is the sender of the message. And really, that's how digital signatures work. Basically, Alice sends a message to Bob, which is not a secret message, but she uses her private key to sign the message. And Bob can then use Alice's public key to verify that the origin of the message is is Alice. And that's how blockchain transactions work. They are signed using public key cryptography. So these transactions are not secret. They're completely public, visible to anyone on the blockchain. But anyone can use the public key of to verify the sender of a transaction, which is very powerful. Similarly, cryptographic hash functions are used a lot in blockchains, and what they basically do is that they are concerned with data integrity. And the idea is to take a variable size input and to pass it through one-way cryptographic hash function to come out with a digest, a fixed size large number representing the input. And this has to have some properties to work. As I've already said, there's a cryptographic hash function, and that should be one way, meaning it cannot be reversed easily. And that is used to calculate the digital fingerprint of the input data. We're mapping, as I've said, variable sized input to fixed size output. So you might have 3 megabytes of input, but you always get out 256 bits of a hash value. And the properties of the hash value have to be that they're pre-image resistant, meaning that we cannot discover, having the hash number, the original message, the original piece of data, right? So you cannot do the inverse of the hash function, or at least not practically in computer science terms. And the second property is what we call second pre-image resistance, which should mean you cannot easily find another pre-image that that maps to the same hash value. And that's something called collision resistance. So you shouldn't, that's very related to second preimage resistance. You don't want collisions in the sense that two texts accidentally or not so accidentally map to the same hash number. The hash number has to uniquely identify the input. Now, of course, if you have larger inputs than you have outputs, there will be some collisions at some point, theoretically, but we want that to be practically very unpredictable and impossible. So it shouldn't happen within a reasonable time frame, and it shouldn't really happen in terms of practicality, even if it's theoretically possible. And that's exactly, these hash functions are exactly what is used in blockchains to link the blocks. Every block is linked to the previous block by including the hash value of the block header. And it's also used in proof of work in this sense, which we'll discover later on in this series. But basically this linkage with hashed cryptographic hash functions provides the immutability property of the blockchain, which is very important. So anyway, nothing else on cryptography that I want to get into now. We'll look at how all this is used in the blockchain in later videos.